Hello physical science student, welcome to video 4 in the series, and this is about alpha decay as promised. Now we're going to say the obvious here. Alpha particles are released during alpha decay. Now just to remind you, when you write alpha, it's like a fish, sort of like that. You can get more pronounced if you like and put the little tail there. Alright, but I'm quite happy to have you draw it like that. Now some people say, that's not a fish, but if we add the eye and a smelly, that's a happy fish. Let's get rid of that. Let's get back to series stuff. Alpha particles are slow-moving particles that are equivalent to a helium nucleus. We've said this before and we're just reinforcing it. It's only the nucleus. Don't confuse, we spent the first topic that we did in physical science was about atoms and how atoms have electrons orbiting around them. We're not saying that an alpha particle is a helium atom, it's a helium nucleus. And as we saw before, the symbol we use for an alpha particle is helium-2,4, and after alpha decay we have to have a change in the mass number of the daughter nucleus. It's 4 less than the parent nucleus, and the atomic number is going to be 2 less than the parent nucleus. And the easiest way to represent that is in an equation. Well, here's a schematic first. Doesn't look any different. Parent nucleus, protons, neutrons, daughter nucleus plus the alpha particle, 2 protons, 2 neutrons, flies off. Bang. But here's our nuclear equation. Remembering we've got our atomic numbers and our mass numbers, we have to have both of those. Here is our alpha particle, and this is our daughter isotope or daughter nucleus, and this is our parent. And so these numbers have to add up. Notice that the daughter, its atomic number is 2 less than its parent, and its mass number is 4 less. And the numbers add up. 89 plus 2 gives you 91. 232 plus 4 gives you 236. Notice that, let's change the colour here. Notice that on this one they've got this guy, and that's a gamma particle. And gamma particle is basically what we call a photon, and that is equal to energy. And so what this is saying is that when this decay occurs, this one decays to this plus this, there's still a little bit of energy left over in the nucleus, in the daughter nucleus, and that daughter nucleus gets rid of that energy very quickly in the form of a photon. That's all that's saying. Now most of the time we don't write that, but I would recommend that you start writing it in whenever you're doing alpha and beta decay. You just add in that just to denote that you know that it's there. Not everyone expects you to write it, but it's good practice to do it. Right, what's next? Okay, here's some facts about it all. So you can read this. I'll read it quickly, just scanning through it. We've already said what alpha particle is: 2 protons, 2 neutrons, exactly the same as a helium. Now what are some of the properties of the alpha particle? Well, they travel fairly slowly. In the grand scheme of things, they don't move very fast. You might think when we do a table of their speeds, it's not very fast. Basically the fastest that anything can move is the speed of light. These guys come out at about 10% the speed of light, which in the world of atomic physics is slow. But they're very heavy. They're the heaviest of the particles that we'll talk about, and because they've got 2 protons, 2 neutrons, so they have a mass of 4, and they cause ionization. And that's the main concern in terms of alpha particles, is that the fact that they're very good at ionizing. They have what's called a low penetration power, and we'll have a video on penetration power coming up. because they're stopped very easily. Because of this high ionization power, they get absorbed very quickly. And so if we categorize it, they're stopped by a small amount of air, so they really only travel 5 to 10 centimeters in air, or a piece of paper stops them. That's not very tough, hey? However, come on, whoa, we went way too far there. However, they're a hazard. Now, in terms of hazards, they're not very dangerous as external sources. So if you have an alpha emitter, which is very high emitter of alpha particles, as long as you don't get very close to it, you're not going to get hurt by it, because the alpha radiation doesn't go very far. However, if you were to pick it up, you could get superficial burning on your skin, which is very similar to sunburn, and so people get that sort of burning. Now, if you were to ingest it, which is not recommended, it would get very close to living cells. And so if you inhaled some particles, it's not very good, because you get it into your lungs, and your lungs are always undergoing cell replacement, so they're living and they're splitting and growing, and so that's not a very good situation. So people have to make sure that if they are working with an alpha emitter, there's no possibility that you can ingest it or you can get close to it. Now, when we work with an alpha emitter, it's sealed, in that it's not a powder or anything, it's just a lump of metal, so it doesn't break off into little pieces, and we use tongs when we handle it, and that gives us the 5 to 10 centimeters of protection. Now, we've talked about the decay equations, and so here's some more examples of alpha decay. This is a different one, uranium-238 going to thorium, plus energy, so you don't have to write the gamma symbol. You could write the gamma symbol. Oh, that's wrong. That's the affinity symbol, is it? I can't remember. Anyway, that's the gamma symbol. But see here, they've written the same equation, but instead they've used the alpha symbol. Wouldn't recommend you do this. The only way I'd let you do that is if you also put a 4 and a 2 there. But really, you should use this symbol for alpha. And you may see some textbooks or on the web, if you're looking for other information, using that symbol. Strongly recommended you don't. Trust me. Right, what's next? That's the end. Next video, we're going to do beta decay. See ya.